All right, 6610. Due to a technical glitch, actually a bozo moment on my end, equivalent to adding one and one, getting three, I had to redo this video. Anyway, so I've already got some of the stuff written out. The two sampling distributions, probability distributions that we've seen so far is Z distribution and T distribution. This is appropriate when estimating or testing a claim about mu, where the population standard deviation is known. The standardized distribution has a mean 0, standard deviation 1. T distribution, again, claim about mu or estimating mu, where the population standard deviation isn't known. Degrees of freedom n minus 1. There are two other sampling distributions that we run into, and I really struggle in teaching 6610, 6620 when to introduce this, but because I want you to think of these as a sampling distribution from which we calculate p-values and from which we calculate critical values and compare test statistics to, I want to present the introduction to this material closely after introducing this, and in the context of sampling distributions and the central limit theorem. So the first one, the chi-square distribution, is defined by its degrees of freedom. And I'm not going to go into how the degrees of freedom are calculated because it depends on the situation. Degrees of freedom for a chi-square test of independence, for example, is the number of rows minus 1 times the number of columns minus 1. Chi-square goodness of fit, it's k minus, anyway, k minus 1. But anyway, there's different scenarios how the degree of freedom is calculated. Now, this will be just one number compared to the F distribution, which we'll see in just a second. Has 2 degrees of freedom, not degrees of freedom equal to 2, but 2 different ones. I'll call them df1 and df2. So anyway, for the chi-square distribution, if we calculate a test statistic, the p-value is the area to the right. In the Z distribution and the T distribution, sometimes we have a left tail and a right tail. That is never the case for the chi-square distribution or the F distribution. So it's really simple with R to calculate. So, let's say we have a chi-square distribution, degrees of freedom equal to 4. And let's say that our chi-square test statistic equals 3.2. So in other words, what we want is we have this non-symmetric distribution, degrees of freedom equal to 4. We have a test statistic at 3.2, so the p-value will be the area to the right of the 3.2. Very easy to find. Again, since the areas at to the right, we need to subtract from 1 because, getting ahead of myself, the p chi-square, the p norm, the pt, the pf always finds area below. So we need to subtract from 1 to accommodate for that. So we have 3.2 degrees of freedom equal to 4. So the p-value in this case would be 0.52. So we would fail to reject H sub O. Now, the critical value approach is a little bit different in that it comes in and finds an F critical, a chi-square critical, and we compare our test statistic to this. So to find the again, you just have to tattoo this to the brain. You have to be able to differentiate between a chi-square critical, which is a critical value. Any test statistic falling to the right is reject. Any test statistic falling to the left is fail to reject. A p-value takes the test statistic only, not a critical value, and calculates the area to the right and compares it to typically 0.05. So if I want to find this chi-square critical, then I'm going to use the Q function. And if my alpha is 0.05, which it typically would be, then the area to the left is going to be 0.95. And let's just say, again, our degrees of freedom are equal to 4. So 9.488 is kind of the line in the sand specific to our test statistic. So you can see in the area in the problem up here, if our test statistic was equal to 3.2, then that would fall right in here somewhere, being in the fail to reject region. It actually turns out that, well, thought I had more paper. It actually turns out that the F distribution behaves, I don't know about behaves, it's not like it's a kindergarten student or something. The F distribution kind of acts similarly, but it has 2 degrees of freedom. Literally. Degrees of freedom 1 and degrees of freedom 2. So let's say for this example that we have degrees of freedom 1 is equal to 3 and degrees of freedom 2 is equal to 7. So this defines an F distribution, which will be much like the chi-square distribution. It won't be symmetric, and all the activity happens in the right tail. So calculating a p-value given an F statistic, a test statistic, equal to, I don't know, 2 point whatever it may be, would be equivalent to finding the area to the right of 2.4 in the F distribution with the degrees of freedom 3 and 7. Easy to do. We use, again, 1 minus, but this time we use PF because we're using the F distribution. The test statistic here is 2.4, degrees of freedom 3, 7. Again, notice we have 2 separate degrees of freedom here. So the p-value would be 0.15, and 0.15 is greater than 0.05, so we would fail to reject H sub O and not have statistical significance. If we're looking at the critical value approach, we're trying to find this F star that I'll call it, this F critical, which separates the reject and the fail to reject. Well, it's simple. Just again, QF, right? And we need 0.95, and we have degrees of freedom. Let's just say 3 and 7. So 4.35 would be the F critical that separates the reject and fail to reject region, right? And previously we saw 2.4, and 2.4 would fall, somewhere there and there, which again is consistent with the decision made on the p-value, but the test statistic 2.4 would fall to the left of the F critical of 4.35. So really, those are the 4 probability distributions that we encounter in 6610, 6620, and 5500 and 6500 if you end up taking those someday, or maybe you've taken them previously. So when you're testing something, let's just kind of go out on a limb here and say when you are testing something, and let's just fast forward into the regression world. If you're testing that beta 1, which is the population slope in a simple linear regression model, All right. So we're predicting y from this model. And we come in and we take an estimate from our sample, B0 and B1. We use that to estimate these two values. Again, we'll study this in 6610. The first thing we have to ask ourselves is why. You would say we set your alpha. No, not so fast. What we have to say at this point is what or which underlying probability distribution, T, Z, chi-square, F, models this problem. And these are the things you depend on me, and I depend on others who have done laid the groundwork for statistics previously. Once we decide which probability distribution defines this phenomena, then we know the distribution that we're dealing with, whatever it may be, defined by its degrees of freedom or its mean and its standard deviation. Then we could come in, we can calculate p-values, wherever they may be. We can calculate p-values and test statistics and calculate confidence intervals. So that's wrapping it up. We will move into, I think the next thing I'll do is take you through an example of running a t-test and how to report the results. And then we'll get into two sample t-tests, then we'll probably get into chi-square, and that will probably wrap up lesson number 1. All right, take care.